All right, howdy folks. In this video, we're going to go over some common reactions to either use an aldehyde or a ketone as a starting material, or reactions that produce an aldehyde or a ketone or some amine products. And so generally, I would consider this a reactions kind of tutorial. And so please go ahead and take a pause here at this stage and try to go ahead and fill in the reactions that are shown on the screen at the moment. So go ahead and pause. As a reminder as well, you should be able to download the PDFs, both of the blank questions as well as the ones that I'll ultimately fill out by using the Patreon webpage, make a pledge, and then you can have access to all the PDFs available. And there should be a link on that in our channel. Okay, so I'm just going to expand this out here, grab the pencil tool, and then talk through some of these questions and answers. And so the first reagent given here is called hydroxylamine, and it's a pretty good nucleophile, and it's nucleophilic on that nitrogen lone pair. And it's going to make a condensation reaction with the ketone, and this will form what we call an oxime. And an oxime is a special form of an imine. And an imine, remember, is some C double bond N containing group. And the oxime is special in the sense that it is an NO containing imine. And it's a special functional group, and it's used for a variety of things, as well as just derivatizing ketones to make sure that that's what you started with in the first place. Okay, the next reaction uses a nitrile as a starting material. And as an instructor, I really like questions where I can have the same starting material a couple of times and ask students a whole series of questions from that same starting material. And in this particular case, there's a lot of these that are asking the student to fill in the reagent. And so we're given the starting material, and we're given a series of different products, and we're asking the student to go ahead and fill in what kind of reagent would produce those products from that starting material. The first one here is an aldehyde byproduct. And one thing I try to encourage people to do is just to identify your oxidation states, because that often will tell us what kind of reagent we need. And as a reminder, our most common kinds of reagents are going to be acids, bases, we have nucleophiles, electrophiles, and then there's oxidants and reductants. And so those are our major kinds of reagents. And in this case, this nitrile is at the +3 oxidation state, and the aldehyde is at the +2 oxidation state. And so if we're going down in oxidation state, then we need a reducing agent. And we can get that by, again, recognizing that there has to be some kind of H bound to that aldehyde carbon. And that H has to come from somewhere. And so the first reagent that we're going to use here is dibol H. And for those of you that may have forgotten, dibol is a special aluminum hydride reagent that has these isobutyl arms coming off of it. So it stands for diisobutyl aluminum hydride. And that's a very special reducing agent that will stop the reduction of a nitrile at the imine intermediate. And then typically upon workup with H3O plus and water, and sometimes people don't like it when you write H3O plus because you can't get H3O plus all in a bottle. And so this might be, realistically HCl in water. It might be another way to think about it. And under those conditions, you end up protonating off and hydrolyzing the imine product upon workup. And so this turns out to be a very clean way to convert a nitrile to an aldehyde, and generally the yields for this kind of reaction are quite nice. Okay, the next step here varies from the first one because instead of ending at the +2 oxidation state, we're going to go all the way down to the +1 oxidation state. And that means that there's 2 undrawn hydrogens there. And dibol is a very powerful reducing agent, but it's not our strongest reducing agent. And so I usually kind of joke with people that the big sledgehammer kind of reducing agent is lithium aluminum hydride. And so if we really need to take something all the way down in oxidation state, I encourage you to think about lithium aluminum hydride. And then in this case, we're probably just going to want to use water to work up the reaction. Remember, if you end up using acid, you'll protonate that NH2 as the NH3 hydrochloride salt, and then it'll be water soluble and you won't be able to extract it out of your reaction. And so at least in this case, one would want to use neutral water instead of HCl and water. All right, the next one's a goodie here. And in this one, we're going to make a carbon-carbon bond, and so that's going to be quite significant. The other thing is, remember, ketones like aldehydes are going to be at that +2 oxidation state again. And so it's kind of interesting that we're going to be going down in oxidation state, but we're also going to be forming that carbon-carbon bond. And so the reagents I would recommend here is methyl magnesium chloride or bromide, so some methyl Grignard reagent. And then the second step, again, much like above, is going to be our HCl and water, or H3O plus and water, depending on how you prefer to write it. And the way that this works, of course, is that the carbon on the nitrile here is an electrophilic carbon, and we're going to take that strong methyl minus anion and attack that carbon with it. And then again, that'll produce an imine, and upon the acidic workup again, that imine will get hydrolyzed to the ketone. All right, rolling right along here. So the aldehyde starting material here is going to end up in this double bond, and it's hard to know which of these benzene carbons were in the starting material, but the good news is this molecule is symmetric. For those of you that are interested, this particular product is called stilbene, and it's kind of a famous di-substituted alkene. Well, the good news is hopefully for those of you that have reviewed how aldehydes and ketones can react, you may be familiar with one of the more famous reactions in organic chemistry, the Wittig reaction. And the Wittig reaction is fantastic for taking either an aldehyde or a ketone and converting it into a double bond. And remember, we need an ylide for this. Now we're given an additional base here, and so presumably that base forms the ylide from the phosphonium salt. And so let's just draw the full phosphonium salt. And so we can start all these phosphonium salts with PPH3+, and then we always need a counterion, and I'm always a big fan of bromine as my default counterion. And then we have to finish the salt with whatever else we actually want to transfer, because remember, the phenyl groups on that phosphorus don't transfer in the Wittig reaction. They end up as PPH3 oxides, which is the byproduct. And anybody who's ever run a Wittig reaction in the lab typically tends to remember this, because you get all this kind of white gunk in your flask when you're done, and that white gunk that kind of has the consistency of semi-dried toothpaste is the PPH3 oxide. Okay, and so here at least we want one carbon on this half and then a benzene ring. And so I think that this benzyl triphenylphosphonium bromide would be a great reagent to actually conduct this Wittig reaction. Now, a couple of interesting things that I'll throw in here just as a reminder is, remember, we make Wittig reagents typically through an SN2 reaction. So if you take triphenylphosphine and benzyl bromide, this one is a great SN2 reaction, and that's how we end up with the salt. And remember that salt by itself doesn't really do anything. What we need to do is deprotonate that salt, and that's where our butyl lithium comes in. And so remember, butyl lithium has the general structure like this, and sometimes we can write butyl lithium as butyl minus and lithium plus. So it's a very strong base, and so we can deprotonate that, and that would make the ylide. You remember the ylide has a resonance structure where it's double bound to carbon. And so sometimes we see the ylides drawn like this. In any event, that phosphonium salt plus butyl lithium should be sufficient to deprotonate it to make the ylide, and then the ylide will attack benzaldehyde to make stilbene. So good for that one. All right, this next sequence here is a two-stepper, and it's going to be the Gabriel synthesis. And so here we have this phthalimide anion. It's a great anion for a SN2 reaction. And so initially what that'll form is the alkylated phthalimide, and then hydrazine removes this, and we'll end up with the amine, propylamine. And the reason that you use the Gabriel synthesis, remember, is if you take a regular old ammonia plus propyl bromide, you end up with a mixture of your primary amine. Then you can end up with some secondary amine. You can end up with some tertiary amine. And lastly, you can also end up with the tetrasubstituted ammonium salt. And so remember, alkylating primary amines is often quite problematic. Either primary amines or ammonia itself have this issue of overalkylation. And so the Gabriel synthesis is one of our classic solutions to that problem. The other one, if you're interested, remember, is to use an azide. And this particular azide would be a very low molecular weight azide. It would be volatile. And one thing I'll remind people about organic azides is they can be explosive. And so if it were in my lab, we would be very concerned about making propyl azide. But thankfully here, we're just representing this chemistry on paper, and so we don't have to worry about that safety issue. Then we can reduce this with palladium on carbon, or you can reduce it with lithium aluminum hydride, or you can actually use PPH3. Same stuff we use for the Wittig reaction ends up with a different reaction, which is called the Staudinger reaction, and that'll actually reduce the azide down as well. All right, so all of those will get us the same amine. And the use of an azide is often thought about as being complementary to the Gabriel synthesis. And in any event, it's one of our tricks for making a primary amine and avoiding this issue of overalkylation. All right, that's going to be it for this video. I think we've covered quite a few reactions here for aldehydes, ketones, and amines. If you're finding these videos helpful, again, please do subscribe to our YouTube channel. That doesn't cost you anything, but at least lets us know people are watching these videos, and it gives us some encouragement to continue making a few more. And so please subscribe now. Also, if you like or would like access to the PDF notes, either blank or filled out, again, you can subscribe to us on Patreon and then access and download all the PDFs. All right, so with that, please go ahead and click on the next video, tell your friends about us, and have a great day.